Hi everyone, welcome to Modern Optimization Methods. Today we will introduce the seventh part of Chapter 7, the second-order sufficient conditions. Now recall that we are trying to characterize or we are trying to solve the constraint optimization problem which have equality constraints and inequality constraints. Now, to demonstrate the second-order sufficient conditions, we need some assumptions. So firstly, we assume that for some feasible point x star, there is a Lagrange multiplier that satisfies the first KKT conditions. Okay? And the second assumption is that we assume for all the directions in the critical cone, we have the following positive conditions, which means that the Hessian matrix of Lagrange functions, they multiplied from left and right by the directions in the critical cone will be positive. So the two assumptions are very essential to the second-order sufficient conditions. With the two conditions here, we can actually get the conclusion that x star is the strict local minimizer of the constraint problem. So if we take a look at the sufficient condition here, the most important one is the second condition, okay? So as we recall that in critical cone, we actually characterize all those undecided directions with respect of function f. And the second condition basically says that the Hessian matrix of Lagrange function, it is positive definite over the cone here, okay? So which is very important. In other words, all the directions in the critical cone is actually an increasing directions in terms of the Lagrange function. Now, we have some remarks about the second-order sufficient conditions. Firstly, we do not need any constraint qualifications because this is sufficient condition rather than necessary condition, okay? The second remark is that we use the strict inequalities in our assumption. In other words, we require that for each directions in the critical cone, the Hessian matrix of Lagrange function should be strictly positive definite, okay? And in particular, if the Hessian matrix of Lagrange function is positive definite, then of course we can see that x star is a strict local solution. In other words, the Hessian matrix of Lagrange function is positive definite. This is a very special case of the sufficient second-order conditions. Now, let's demonstrate two examples. The first example contains only one equality constraint. And the aim here is that we try to identify or we try to prove that one solution x is a strict local minimizer. So we first write down the Lagrange function here, and then we can calculate or we can solve the KKT condition to get the optimal solution or the stationary point x star with the Lagrange multiplier half 1/2, okay? Then with this x star and the lambda star, we can characterize the critical cone. And we can also calculate the Lagrange Hessian at x star. So we take second-order information with respect to the Lagrange function, and we find that the Hessian matrix of Lagrange function is an identity matrix, which means that it is positive definite for all the space in Rn. Therefore, it also holds for any critical cone. So here we do not need to characterize the critical cone because this is positive definite, all right? Therefore, from here, we can conclude that X star is already a strict local minimizer of this problem. Okay, now let's take a look at the other example. In this example, if we take a look at the objective function, we can see that this function is actually goes to infinity when x tends to infinity. In other words, by the constraint here, okay, so the constraint is actually the whole space, then we take out one disk, okay? Then the constraint is unbounded region. And with this unbounded region, the objective function is actually not lower bounded. In other words, there is no global optimizer for this problem. However, in terms of local solution, as we will show later, that we could identify a strict local solution for this problem. Okay, so this strict local solution, we can consider the KKT condition and the second order sufficient condition. By the two theorem, then we can find one or at least one strict local minimizer. Now let's show you the details. So firstly, let's take a gradient of the Lagrange function. So this gradient of Lagrange function takes the following form, and if we do Hessian matrix, then we can find that this Hessian matrix is actually related to the Lagrange multiplier. So if we solve the KKT conditions, then we can find that X star, which is 0 and 1, with the Lagrange multiplier actually satisfy the first order optimality condition. So with X star and lambda 1 star, we can characterize the active set. Okay, so the active set is actually the inequality itself. Then we can characterize the critical cone. So the critical cone here is that we write down here by just ignore how we derive the linearized feasible direction. Okay, we give directly the critical cone here. And if we submit the lambda 1 star into the Lagrange function, then we can get the formula for the Hessian matrix like this. So for this Hessian matrix, you can see that Hessian matrix is not positive definite because it got one diagonal element's negative number, right? Now for the critical cone, it has the first component 0, the second one is freedom, okay? Omega 2 is in Rn, so it is freedom. Now let's check whether the second order sufficient condition holds. So we need to check for each direction omega in the critical cone whether the product here will be strictly positive. Okay, so we substitute the form of omega from the critical cone into this formula, and we can see that although the first diagonal elements in the Hessian matrix is negative number, however, our multiplication will actually cancel this out, and we will reach a strictly positive number here. Okay? In other words, the condition in second order sufficient condition holds. Therefore, we can get that this X star is indeed a strict local minimizer. Alright, let's make a brief summary about this part. We have introduced the second order sufficient condition and demonstrate two examples to show how it works. Okay, we stop here and see you next time.